Can you hear me?
Yes.
Oh, okay. So, my name is Gerardo Ortiz from Indiana University, and, it's always a pleasure to introduce Frank. Indeed, Frank, it's an outstanding, he's a very good friend, outstanding guy, but in particular, he is the first recipient of the Herman Kummel Early Achievement Award, okay? And, this is very special for several reasons. One of the reasons is that this was one of the few occasions that Herman Kummel was present, okay, there, okay? Second is that, indeed, Frank has set such a high standard, okay, of excellence for this award that now every year is more and more difficult, okay, to select the right guy, okay? Fortunately, in the future awards, we were fortunate to get outstanding candidates. Indeed, that tradition will continue, certainly. So, Frank is originally from Belgium, and he did a postdoctoral PhD work at Leuven, the Catholic University of Leuven. And later on, he moved as a postdoctoral fellow to the group of Ignacio Cirac, where he continued doing magnific work. And after a few years, he moved to Caltech, more specifically to essentially the Institute for Quantum Information that, John Preskill is the head of that institute. And almost a few years after, it was just 1 or 2 years, the impact of his work was such that he got a full permanent position, a full professor position at the University of Vienna. Okay, that was in recognition, to the type or high level of work that he was doing in the context of quantum information and, I would say, condensed matter physics. In 2012, he moved back to Belgium, where he is currently leading a huge research group in the University of Ghent. Let me tell you a little bit about the kind of work that Frank does. He does, very original work, but in particular, he works on developing techniques and methods that are, that have some sort of quantum information theory flavor, and he adapts those technologies essentially to study classically simulations of strongly interacting problems, NP-hard problems. Okay, so that is one of his main strengths, and he had been, played leading roles in development of several of these techniques. He has, advanced variational techniques such as, PEPS. PEPS was one of the first generalizations of the matrix product states to higher dimensions. And later on, he generalized these things to tensor networks in many different flavors. And this is what I think he's going to talk about today. So with this, I pass the microphone to Frank. So thank you very much, Frank, for being with us.
Thanks a lot, Gerardo. I think you were way too nice. And I'm always suspicious when people are so nice to me, it feels like they need something.
I have bad things to say about you. I have bad things to say about you.
No, you were exaggerating a lot.
Yeah.
But let me try to share my screen. Okay.
In particular about soccer, I have very bad things to say about you.
That's true. That's true. Anyway, it's a great pleasure to be here and a great honor. I still remember indeed this Kummel Award. This was like the first time that that was actually a big thing, and one of the reasons, of course, that I got kind of this position in Vienna and all this. So I'm very happy and glad that I had the honor to do this. So today I will talk about the continuation, basically, of the work that I did a long time ago. That started indeed with Ignacio Cirac and then with John Preskill, and then after that. So I started very ambitiously with. I thought I will make a great talk, and I spent all the time in making my front slide. Basically, I wanted to have kind of a nice picture of what is actually what is it that tensor networks do? What is it? Is there like a simple way of conveying this to general public, let's say to my mother. And of course, I wanted to have a picture of something like a spin liquid, something very chaotic. This is Jackson Pollock, so it's kind of a beautiful, huge painting. It's like it really symbolizes a spin liquid, and it's very complicated to see. And what a tensor network does is actually take out this complexity and make some kind of harmonic one-dimensional structure out of this. So this is in many ways the essence of tensor networks is trying to find order and harmony and actually something like entanglement spectra in very complicated superpositions of spin liquids. And of course, so what I took here is one of the most famous music pieces of music. This is the Art of the Fugue of Bach. So it has lots of repetition, lots of structure. This is basically what tensor networks aim to do, kind of out of the chaos and the complete disorder of very complicated, strongly correlated quantum many-body systems, try to relate them to some lower dimensional system in which there is much more order and where we can actually do the physics. Okay, so anyway, so the outline of my talk, I will basically talk about some recent developments that we have been doing in my group, both on the computational aspects and the theoretical aspects. But of course, these theoretical aspects will then again also touch onto the computational aspects. But in general, what these tensor networks do is we try to unravel the entanglement patterns in strongly correlated quantum systems. Okay, this might sound a little bit pretentious, but I will try to make sense out of this. So. What I will not talk about is actually very exciting recent developments in the field of tensor networks that I have personally not been really involved, but like there's this notion of tensor trains, which is basically tensor networks, matrix product states that are used a lot in applied mathematics. Things like how do you solve high dimensional differential equations, Laplacians and things like that? How do you actually use tensor networks for describing things that people in the quantum gravity community are interested in, the holography, all these things. This seems that actually these tensor networks provide extremely nice toy models for understanding some deep truths in this field. Also, like how do you simulate noisy quantum computers? So the state-of-the-art methods for doing this. There were lots of very exciting results about this in the last years, and trying to kind of optimize and coming up with better and better ways of constructing tensor networks that actually correspond to the quantum circuits that people have in these noisy quantum computers that also Roger was talking a little bit about, and also like indeed connections between tensor networks and these neural network states that Roger was talking about. There's lots of interesting interplays between this, but I will not talk about this. I just wanted to mention that there's lots of I wanted to give you kind of an overview of some very exciting developments in this field. But anyway, what do tensor networks do? So they basically provide the syntax of a language with a vocabulary consisting of qubits and entangled pairs. So what I have here is something that you probably all kind of recognize. It says the resonating valence bond state of Anderson and collaborators, and so basically what you have is a superposition of all possible kind of singlets in this spin liquid, and the way somehow we want to represent or the power of tensor networks is that actually this superposition of all these possible representation of all these possible configurations can be captured by a very simple tensor. Okay, so basically you take the superposition of the singlet being here plus there and so further. This all looks like a very complicated way. It looks very complicated to write down such a superposition in a tensor network. Well, it turns out that tensor networks are somehow devised, and this is particularly the PEPs, somehow can capture that with something with very low bond dimension. So these wave functions turn out to have very low entanglements, very small amounts of entanglement, and this seems to be a general feature of all these kind of ground states of strongly correlated systems. There's very few entanglement in these systems, and this entanglement can perfectly be captured by looking at this from the point of view of these superpositions of singlets, of entangled pairs, and taking superpositions of this is actually a very easy kind of thing to do using these tensor networks. Okay, so basically what these tensor networks do is they look at a problem. You have, for example, a spin chain, a one-dimensional system, or you have a two-dimensional system, or you have something like a holographic system. And depending on what structure you have, what the geometry is of your quantum many-body system, you use an ansatz that is very well tailored toward capturing somehow the entanglement structure. So like in 1D, somehow the entanglement is always mostly kind of concentrated around nearest neighbors. So these nearest neighbors are very strongly correlated. The things that are a bit further are less correlated, and that makes that actually the wave functions that describe ground states of low energy states of strongly correlated systems have a very particular entanglement structure that can be completely captured by representing them with matrix product states. So basically you have these blue degrees of freedom. So these are like your physical spins, and you have these red degrees of freedom, and these are like, this is the shadow world. So this is the world. So this is like an extra ancillary kind of Hilbert space in which your entanglement degrees of freedom live. And as you will see, basically what this amounts to is this holographic mapping in which you kind of go from a full big one-dimensional system with an exponentially large Hilbert space. What these matrix product states do is map this to some local virtual shadow world that is actually very low dimensional. And the same happens in this kind of 2D cases. This is a tabs here. Okay, so what is this shadow world? I don't know how to kind of put this there. Okay, so the whole idea is that that ground states or low energy states of strongly correlated systems can have a representation, a lower dimensional representation. So you map basically a ground state problem of an n-dimensional system to an n-1 dimensional non-equilibrium problem. Okay, so the example, actually, the most physical example is something that is the continuum version of a matrix product state. It's called a continuous matrix product state. What this actually describes is, so the techniques to describe such continuous matrix product states turn out to be in one-to-one correspondence with the way in which you represent kind of atoms or describe atoms that are living in a cavity. So basically what you have is, you have a cavity in which somehow there's some dynamics. There is kind of degrees of freedom leaking out of that cavity. And if you kind of describe the wave function that comes out of this cavity, all these degrees of freedom are entangled because they interacted all with the same degrees of freedom in the cavity. The dimension of the degrees of freedom in this cavity is exactly this bond dimension that Roger Nalko was also kind of alluding to briefly. So you have some kind of non-trivial dynamics going in the cavity that represents the number of degrees of freedom. And then somehow all these outside, all these qubits, all these degrees of freedom outside are entangled via the same thing. And it turns out that the mathematics of describing such a system, like the wave function of the particles that leak out of this cavity, is in one-to-one correspondence with these matrix product states. Okay, it's exactly the same mathematics, it's exactly the same physics, actually. And this is why we say that actually this is, of course, a non-equilibrium system, describing a non-equilibrium system in 0D. And the non-equilibrium system, this cavity kind of system, has all the features that matrix product states have. And this is exactly what we mean with this holographic principle, the shadow world. Actually, it's much easier to describe a non-equilibrium system in 0D than a quantum many-body system in equilibrium in 1D. Okay? Because there's, of course, like you go from something non-equilibrium in a very low dimensional space to something equilibrium that is exponentially large. And that's the whole point of the success of tensor networks, is that this is possible. Okay, so what happens actually in 2D? Well, I of course couldn't, I had to use my picture again. So this is exactly what is happening also in 2D. You map basically a two-dimensional quantum spin liquid to a one-dimensional effective theory that is non-equilibrium. And this theory you can actually simulate now using matrix product states. So there's something like all these tensor networks that build on top of each other. You kind of simulate a 2D system by actually mapping it to a 1D non-equilibrium system that on its turn you can simulate this 1D non-equilibrium system by using matrix product state techniques for which you map it to a zero-dimensional system. Okay? And the whole point is that actually all these steps are in some sense understood, and it is understood that indeed all these wave functions on this shadow world can be represented efficiently using all these techniques. And this is also somehow, this both gives, as we will see, actually rise to very powerful numerical algorithms for simulating these strongly correlated systems, but also to some interesting theoretical ideas of how to understand exotic phases of matter, such as systems that exhibit topological quantum order. Okay, so what is actually from a numerics point of view, but because at the end this is a session that is supposed to be about numerics, what are all these algorithms that people have? And there's a whole wide variety of different algorithms for optimizing these, because at the end you can understand these tensor networks as variational wave functions with respect to, well, the parameters are basically the local tensors. and you want to optimize these tensors variationally given somehow a global Hamiltonian. So this is really the Hamiltonian picture that Roger was talking about. Okay, and so what is actually going on is that very similar to somehow this neural network, you actually work on a manifold. So these tensors, they parameterize a non-trivial manifold with very nice kind of features. It turns out that these are Kähler manifolds, and there's lots of somehow these techniques of differential geometry that you can use and understand to understand the structure of these manifolds. But so what you get is actually a very low dimensional manifold in this huge dimensional Hilbert space, because this is exactly the whole problem of the many body problem, is that your Hilbert space increases exponentially with the system size, and these tensors allow you to map this to a low dimensional variational manifold. And what you do is basically project all the physics. While you would like to evolve the Schrödinger equation, you project that physics onto that manifold. So the only difference is that you start with some state on the manifold, you evolve with your Hamiltonian, and then project somehow this h times psi of a, which is a direction in which you want to move, onto the manifold. So you just put an extra projector here on that manifold, and then you get basically a differential equation for your tensors on the manifold that stays on the manifold, by which you can now do optimization. And actually all the state-of-the-art matrix product state, PEPS algorithms, or even NERA algorithms, they basically work along these lines. That in some sense, this is a way of approximating somehow these kind of differential equations. So get a differential equation, typically differential equations, you get kind of non-commutative terms, and you have to kind of use splitting equations, well, all the different ways, whether it's DMRG or NPS or PEPS. So this is actually all different ways in which you will split and which you will solve at the end this differential equation. Okay, but it provides a very nice kind of understanding of this, and it has actually this time-dependent variational principle that I developed with my student and a postdoc and our colleague Jutta Hagemann has turned out to be a very kind of powerful way of understanding the physics of this whole this whole framework of how to understand all these optimization algorithms. Okay, so what is still the central challenge, and this is still the central challenge that started actually when we wrote first this paper on projected entangled pair states in 2003 and 2004. There's still somehow a very hard, and there's still lots of progress needed, but there's also lots of progress made in optimizing these wave functions, especially in the higher dimensions. So as you all kind of know, there's still the Hubbard model is not solved. Okay, but we'll probably not what does it mean to be solved. I really don't know, but of course you want to have a very kind of well-controlled numerical method for dealing with such systems, such as the Hubbard model in 2D. But of course, there's a whole wealth of other kind of systems that we are interested in simulating, just like, for example, these Rydberg atoms. And then there's lots of, there's a huge kind of need, as far as I understand, both in condensed matter, but also in high energy physics, to develop methods for simulating ground states or for finding ground states of strongly correlated systems. So what are the state-of-the-art methods for dealing with this? And there's still lots of possible improvements, but there's also lots of progress made in the last, let's say, 3-4 years has been made. Is really somehow to implement this whole boundary idea, these boundary matrix product state methods, and this gradient tangent plane methods to optimize these PEPs. It has turned out that it has been proven that indeed the previous naive kind of methods for optimizing PEPs were certainly not always kind of giving you results that were, from a variational point of view, optimal. So there was these things like called the simple update and the full update and all these things. It turns out that these are really not these are not good enough for many kind of the applications that we have in mind, and these gradient and tangent plane methods that are basically built on top of this differential geometric point of view of this TDVP, this time-dependent variational principle, turn out to give you the right kind of systematic way of improving these algorithms, and using somehow these ideas. There's many things like excitation spectra on top of the ground state, like these are, of course, from the point of view of experiments, very important kind of features. All of these can now be very easily kind of extracted. So, for example, this was for some Ising model in the transverse magnetic field. We also have done it for Heisenberg models, and I will kind of show you more results from other people. Okay, so what has been actually a very important development that was first realized by Tak-Sang, Lei Wang, and collaborators is actually that all these tensor network methods benefit a lot by using differential programming. So there is something, this is an idea that comes from machine learning, but it's actually much older than machine learning, that tells you that whenever you have a cost function that you can calculate efficiently, that actually at the same price, at the same cost, you can also calculate basically the derivative of that kind of cost function with respect to the parameters that you have. And this is an idea that is called basically backwards differentiation, or this is also called automatic differentiation in the machine learning community. And it turns out that this is extremely powerful to kind of come up with much more. It makes programming all these algorithms, these PEPS algorithms, and actually also matrix power state algorithms much simpler. Okay, so it makes that actually things that used to be kind of involve lots and lots of kind of effort in programming, like these gradients, like we did, as actually like Lawrence von Straten did this. It turns out that actually using this differential programming ideas from machine learning, you can speed up these algorithms enormously, and not just speed up, also the programming itself becomes much simpler. To me, this was actually kind of a bit of a shock when I learned about the fact that indeed, whenever you have a cost function that you can calculate efficiently, that you can also calculate the derivative of that cost function at the same cost, basically by making smart use of backwards differentiation techniques. But for example, this is the Heisenberg model that you can do now. You can see somehow these simple update and full update. These are like the usual techniques that PEPs were used up to like a few years ago, up to 3-4 years. They really kind of the energy kind of the relative errors in energy for the same bond dimension are much larger than you get with all these gradient methods, these gradient techniques that were kind of developed, by Lawrence von Straten, Philippe Corbeau, and Lei Wang and collaborators. And also somehow now you can kind of look at, so finally somehow things like the Heisenberg model, of course, for which there's no sign problem here, for which basically quantum Monte Carlo gives you the state-of-the-art results. We can finally kind of match this and do some finite size scaling now with some entanglement scaling methods. You can actually extract and get results that are really kind of on par with what Monte Carlo kind of techniques does. So for example, this is another kind of instance, or another example of recent progress in these PEPS algorithms. This is really like simulating the Hubbard model. The Hubbard model in 2D. In this particular case, it's at half filling, and such that you can actually again compare with quantum Monte Carlo, and you can do this for different values of your kind of interaction strength in the Hubbard model, and you basically can calculate gaps. You can calculate somehow response functions, and all of these things start to work and seem to make perfect sense and actually give more precise results, certainly for things like these dispersion relations, and you get actually much more precise results, as far as I understand, than what you get with Monte Carlo techniques. And of course, the big advantage of these methods is that you don't get sign problems. Okay? So you really can really kind of go to the regime in which somehow quantum Monte Carlo techniques don't work. So let me kind of talk briefly now. I'll go to the second topic of the computational aspects of tensor networks, namely what happens actually when you want to simulate critical systems, because this is an obvious kind of critique that you could have, is that you could say, all these tensor networks, they are low entanglement kind of methods, but why would they still work if you kind of have violations of the area laws? What happens if somehow you kind of look at critical systems? Okay, so indeed, the entanglement degrees of freedom in critical systems, they are fluctuating much more. So you get things like violations of the area law. But and the question is, can you still capture this? Can you still deal with somehow these issues with these tensor networks? How can you, or is it possible to develop something like a theory of scaling, of entanglement scaling, similar to the finite size scaling methods of Cardy? So the genius of Cardy was basically to understand that indeed, instead of simulating a critical system, you can just put somehow a critical system on a finite system, on a finite grid, such that there is actually a gap, and then study how that gap kind of changes as a function of the system size. And it turns out that this is much more powerful than actually simulating immediately somehow the critical system. So what you basically do by putting it on a finite size system, like usual exact diagonalization methods, is really kind of you perturb your system such that you open a gap, and then you kind of see how the system kind of behaves when you close the gap. And the basic premise in all these tensor networks, and it's only very recently that actually this is really understood better, although it builds up on work of many people like Nishino, Jan McCulloch, Luca Tagliacozzo, Frank Polman. Many people have worked actually on indeed understanding this concept of entanglement scaling, but somehow I think there's only in the last kind of years that we really got this kind of to work also for not just for matrix Planck states, but also for PEPs. And I would like to briefly kind of talk about this. So the whole premise is that indeed, if you work with a finite bond dimension instead of somehow the infinite bond dimension or the exact wave function, what you do is not simulate the exact system that you're kind of the exact critical system that you're supposed to simulate, but you kind of have added a relevant perturbation to the system. Okay, so and by increasing this bond dimension, you basically decrease this relevant perturbation, and you're interested in how this scaling works. And in some work of 2 years ago from Bram van Ecke, a student of mine, so we took this well, he realized actually that this is a very important or a very powerful idea, is that actually you can both. So the typical simulations of critical systems were done while you kind of simulate for a certain set of parameters. You try to make your bond dimension as large as possible, and then you take a different set of parameters for your magnetic field and do again try to extrapolate as a function of your bond dimension. And then these extrapolated kind of results, you will extrapolate them again a second time to at the end get somehow your scaling analysis. So what Bram van Ecke actually realized is that this is not very kind of this is not very efficient. You can actually do a double scaling at the same time. So working with finite bond dimension and somehow changing your parameters in your Hamiltonian at the same time, all the data that you can have, all the data that you can get, you can actually use it for simulating this one critical point that you're interested in. So you don't have to first extrapolate and then the extrapolated results extrapolate again. No, you can actually put all these results together and do one big extrapolation, and you get basically something like double collapses of your wafers. So for example, this is for a 2D POTS model. So it turns out, of course, all these tensor networks, they both work for stat-mech models and for kind of quantum models, like a stat-mech model in 2D is very similar to a quantum model in 1D. So a critical system in 1D is basically a critical stat-mech model in 2D, and all these techniques kind of work at the same time. But anyway, so by carefully looking at these entanglement degrees of freedom and coming up with some scaling ansatz where you plot everything as a function of the correlation length, it turns out that you can get beautiful collapses and therefore extrapolate your results in a much more precise way than you could do. So then we started thinking, okay, but what happens now if you want to simulate also like field theories? Okay, so it's like critical spin systems. This is basically your UV physics. Your UV scale is 1, your IR scale goes to 0. But gap spin system, of course, for which DMRG and all these things work, basically give you exact results. This is both when somehow you have UV scale and an IR scale that is not 0. But what happens if you kind of want to simulate quantum field theories is that you have also UV scale to worry about, and so all these things together make it actually very non-trivial to try to understand how should I be able to, by making use of all this entanglement scaling, is it actually possible to simulate somehow a quantum field theory? So what does it mean in terms of these tensor networks, in terms of these bond dimensions, to actually take the continuum limit of a field theory? And this turned out to be a surprisingly hard problem. That this turns out, I think, also very relevant for quantum simulators, like the kind of things that Roger was talking about. So how will you, if you say that with a quantum computer you will simulate a quantum field theory, well, you must be sure actually that you will discretize it, you will put it on the lattice and so forth, but you want to be sure that there's no relevant kind of perturbations that you added, such that if you take the continuum limit, that you're actually simulating the theory that you want. And this is something that is very subtle and actually not so easy to deal with. And turns out that with this tensor networks we have, well, using these scaling methods and so forth, we have been able, or certainly same person, Bram van Ecke, was able to resolve this. And so basically we looked at lambda phi to the 4, the simplest, basically non-trivial critical quantum field theory, which for surprisingly, so this is basically, you would say, the Ising model of the quantum field theories. Now in 2D, like lambda phi to the 4, even the critical point somehow of that model was only known up to a few years ago, up to, let's say, maybe 2 digits. So there's not even known where the critical point was. And using somehow these scaling techniques, we were able to kind of extract these kind of things. So what is very interesting is actually, if you kind of start simulating such field theories, is that there's 2 contributions that actually take care of that make sure that you need lots of entanglements to deal with it. So first of all, there's the UV scale, which is basically something like a central charge 1 contribution to the entanglement entropy. And then there's, in this particular case, this is in the Ising universality class, there's on top of that somehow the central charge 1/2 contribution from somehow your IR physics at the critical point. If you wanted to see this, if you simulate somehow these models with tensor networks, you should see both contributions. So there's like, whenever you V scale that goes to infinity, you need basically a critical theory or a critical theory if you put it on the lattice. But additionally, then there's an extra level of criticality at the critical point of your CFT. And so we're able to do this and well, using some scaling, and then you have again something like a double collapse. So you have all these kind of different parameters. You have to collapse all this data on top of each other. And using this, we were able to kind of pinpoint basically where the critical point is of lambda phi to the 4 theory, which is basically, to me, this was a shock also that this was not known very precisely, more precisely than this. But this basically locates where is the critical point of this lambda phi to the 4 theory. Okay, so I'm the next question is then, of course, what happens in 2D? How you kind of how do you come up with all these kind of things where either 2D classical or 1D quantum, but now you want to also come up with a scaling hypothesis for simulating these PEPS wave functions, for simulating quantum critical points in 2 + 1D or 3D sub-mech kind of problems. And at first sight, this looks like a much harder problem because there are basically 2 relevant perturbations. If you kind of look at how these methods work for simulating PEPS, you first have to approximate the eigenvector of the transfer matrix of your 2D transfer matrix. You have to kind of approximate this 1D kind of system with a certain finite bond dimension. And of course, the PEPS itself has a finite bond dimension. So there's like 2 parameters, 2 bond dimensions that enter the whole kind of picture. And it looks like this will be much harder. It will be much harder to actually come up with a scaling theory. So, but nevertheless, we came up with something like a very simple scaling hypothesis is that the bond dimension of your PEPS and the bond dimension of the MPS that you use to approximate the contraction of your PEPS, you can actually, it doesn't matter. The only thing that actually matters from these 2 parameters is the effective correlation length that is induced by these 2 parameters. And if you kind of simulate a system that is close enough to your critical point and the correlation length is the same for different D and chi, you're effectively looking at exactly the same model. And indeed, it turns out that this kind of scaling hypothesis works extremely well and gives like a huge boost of actually being able then to simulate these critical points, because you will need much less data than before for actually doing the scaling. Okay, so now you don't have to first kind of extrapolate in chi and then in D. Now you can do these extrapolations all at the same time. So every data point that you do, even data points with very small D and chi, you can actually put in your kind of data collection and then do the finite size scaling. Somehow the data collapses and actually extract your well, do somehow the scaling limit to the limit where your correlation length is infinity. So for example, this we did for 3D dimers. So it's a sub-mech model of 3D dimers. It's famous and all these collapses work extremely well. You can also do this for the 2D quantum Heisenberg model. And indeed, somehow all these collapses, all these scaling hypothesis things work. And that means that actually now we are basically starting to be in shape for simulating quantum critical points in 2 + 1D. And indeed, somehow these results that I show you here, they basically prove that it is possible, and it is possible actually without a cost that is too kind of large or too kind of extensive. Okay, so if you would be very critical, you say, yeah, but quantum critical points, what we want to simulate is basically Fermi surfaces. Well, we also, turns out that actually even there is, it's also possible. So we looked at somehow several kind of systems with Fermi surfaces. Actually, we looked at cases for the moment that are just free fermions, but nevertheless, you can represent them with PEPS wave function with free fermions. And we look at basically what is the bond dimension scaling that you need to capture such that you basically get the right physics, that you understand basically how to approximate somehow the ground state of some system with the Fermi surface using a PEPS. And it turns out that indeed also there, the scaling is very favorable. Okay, so you can actually approximate somehow the physics as a function of the bond dimension, and then extrapolate somehow this bond dimension, and you will get actually the physics of your system with Fermi surfaces, right? This was always a big critique that we got from condensed matter people, that in tensor networks, well, you're not even able to do kind of Fermi surfaces. Well, it turns out that if you do scaling right, it is actually possible to get this. And actually, for some critical points, of course, it's harder than for others, but somehow the general kind of premise is that indeed, somehow by doing this scaling, the entanglement scaling right, we can approximate somehow systems with Fermi surfaces. Okay, so let me summarize actually the first part of this talk. So there's, I would say that actually the numerical development of PEPS algorithms, so these are basically the two-dimensional versions of DMRG as kind of originally kind of devised by Stephen White. These PEPS algorithms are basically do this for higher dimensions. This is in full swing, and there's still fundamental, like lots of fundamental truths or techniques or tricks to be found and to be discovered actually. So the central challenge is to develop more efficient PEPS algorithms, but and to put somehow this entanglement scaling that I just talked about, actually to put it on a better kind of on a better sound or a sound theoretical basis, or a free theoretical basis. But it seems somehow that these things work very well, and I'm very kind of optimistic that somehow it's clear that the field is advancing, but much slower than we originally kind of anticipated. Okay, so let me kind of go to the second part of this talk, which is actually about the theoretical aspects, because I would say this is the really kind of nice thing and the unique thing of these tensor networks is that they do not only provide somehow a very nice variational techniques or variational framework for dealing with systems that we don't really have other techniques for to simulate them. It also provides lots of theoretical insight into the structure of these wave functions. Okay, so especially the theoretical aspects that are most fascinating that we have been working most on in the last years is actually to try to understand the symmetries and dualities, like how are symmetries of your physical system, how do they affect somehow the entanglement degrees of freedom? How does somehow this shadow world, this lower dimensional world in which somehow everything is much cleaner and harmonic, how does that reflect actually somehow the physics or the phases of your full kind of systems? And it turns out that actually by doing this, there's lots of these tensor networks seem to provide somehow the lattice versions of these topological field theories and also conformal field theories. There's lots of things that we are currently discovering and trying to understand. Okay, so for people that are interested in these theoretical ideas, so together with Ignacio Sirac, David Perez Garcia, and Norbert Schuch, last fall, we kind of wrote a review paper that will be published soon in Reviews of Modern Physics, which is exactly about the theoretical aspects of matrix Florak states and actually these projected entangled pair states. So basically, there's a whole kind of also introduction. There's the history. There's basically connections with RG. What is the RG and all these kind of in this density matrix normalization group. Why is there basically something like a notion of RG? How do you classify phases of matter in terms of symmetries? What happens with fermions, and so further. And but the thing is that that somehow there's a very kind of nice theoretical understanding of these whole tensor networks, and this is completely built on something that is called the fundamental theorem of matrix Florak states, or the fundamental theorem of PEPS. And I would like to briefly kind of introduce this to you, such that somehow as a way of motivating somehow or trying to convey somehow the theoretical basis for the fact that we can really understand strongly correlated, non-trivial strongly correlated phase of matter using somehow this tensor network language. Okay, so what is this fundamental theorem of tensor networks? It's basically a way of relating two matrix Florak states to each other. So if I have one matrix Florak states, or as you will see, this is the same for the PEPS, and I have another kind of matrix Florak state, this means my global wave function is the same. Okay, so I have a global wave function that is represented by one type of tensor, and I have actually a different representation of that same tensor. Now, this is true if and only if these tensors A and B that represent somehow these matrix Florak states are related by some intertwiner X. Okay, so that there's some object X. So what this means is I have a tensor here with 3 legs, and if I multiply this leg with this matrix X, that is equal to basically multiplying the right leg of this tensor B with X. So basically what it tells you that if I come with this X and I pull it through this A, it transforms an A into a B. Okay, so this kind of direction is very easy. That if this is true, it's very easy to see that psi of A has to be equal to psi of B, because this is some kind of just a basis change in your entanglement degrees of freedom Hilbert space, and of course the basis in which you work is completely irrelevant. Okay, but what is much more non-trivial is the other direction, that actually global properties become somehow completely kind of captured by making local claims. And this is the whole kind of idea, and this is a very powerful kind of idea, that the mathematical somehow of the mathematical framework for describing such equivalences is actually turns out to be category theory. So that actually, if global wave functions are equal, what does that actually mean for the local descriptions of these wave functions, so the local tensors? So global wave functions are equal. Well, that doesn't mean that the local tensors are equal, but they have to be equal up to some equivalence relation. Yeah, it turns out that all these up to equivalence relations has some is part of a huge kind of field in mathematics that's called category theory, but was also discovered originally in the context of quantum physics in terms of topological field theories. Okay, so and if we kind of restrict this, we say, like, look, I have kind of a global state that is invariant under global symmetry. So if I multiply every one of my physical spins with the same unitary, and that state has to be invariant. Well, this basically theorem tells you that if I have a U, so I act with the same U on all my spins, like, and I have an SU2 invariant state, then somehow the ground state wave functions, the wave function describing this thing, must have a property that if I act with a UG here, there must be a matrix XG such that XG AUG is A times XG. So basically what it tells you is that it's XG, that there must be some reflection of somehow the symmetry operator on the virtual level, that indeed sees that somehow that takes care of the fact that your global wave function is symmetric. Now, the fantastic thing, and this was originally, I think, first really understood by Xi Chen and Xagan Wen and collaborators, is that somehow this X of G, so this representation of your physical symmetry on the virtual levels, does not have to be the same representation as the one on the physical level, but can actually be something that is called a projective representation. Okay, so it's, for example, on the physical level, you could have an SO3 symmetry, like for a spin 1 Heisenberg model, but on the virtual level, you could have an SU2 kind of group. And SU2, as you all know, is not equal to SO3. There's some kind of, they are topologically kind of distinct groups. There's no kind of way of relating now that they even have a different number of elements. So what this SU2 is basically a projective representation of your physical degrees of freedom. And systems that are represented by different projective representations cannot be analytically or not kind of adiabatically be continued into systems that have kind of two different representations. And it turns out that all these different projective representations of a certain kind of symmetry group are classified according to the second cohomology. Okay, so there's something like, and this understanding of this fundamental theorem has actually allowed to completely kind of classify all these so-called SPT phases of matter in 1D. Okay, so basically the whole premise is that ground states of gapped quantum spin systems can be captured by matrix Floyd states. So this is basically follows from the proof of Hastings and many other kind of proofs. And these matrix Floyd states, if somehow they have a symmetry, must kind of transform, or the entanglement degrees of freedom must transform according to some kind of representation. And if these representations are incompatible with each other, there is no kind of adiabatic way for kind of continue for mapping one of these wave functions to another one without going to a phase transition. Okay, so this is something that is very easily understood by looking at somehow this shadow world, this virtual degrees of freedom, this entanglement degrees of freedom. How do they kind of transform according to your well, how do they transform? What are the symmetries there? Turns out that actually the 2D version, the PEPS version of this is much richer, and this is basically the content of most of the research that is being done in this field of this theoretical research on trying to classify phases using somehow these tensor networks. It turns out that this fundamental theorem, if I have a psi of A and a psi of B and they're equal to each other, it's not that there is just like an X that I can pull through that maps A to B. Turns out that we have to introduce a completely different object. And this is actually another tensor object that lives purely on the virtual world. So there is this is very, very similar actually to something like a Wilson loop, but it's a Wilson loop that acts purely somehow on the virtual degrees of freedom. And if you kind of take this matrix product operator, so everywhere you have a crossing here, you have to put a tensor. And if you kind of pull this tensor through your kind of like, this is the A tensor, this is the B tensor, you will basically map one state to the other one. And this is, in some sense, the equivalent fundamental theorem of PEPS, which has actually not been proven in full generality, but we believe that this should be the fundamental theorem. So I should have put quotes here around this theorem. And it turns out that if you want to study, therefore, kind of topologically ordered systems like this SPT phase, but also truly topologically ordered systems in 2D, it turns out that this is completely captured by studying somehow the representations induced by these matrix product operators. Okay, so it turns out that somehow topological order is witnessed by having non-trivial of these symmetries. So whenever you have a non-trivial topological phase of matter in 2D, this will go hand in hand with a non-trivial kind of symmetry that is represented by such a matrix product operator. Okay, and things like having topological phases of matter that somehow there's no local order parameter. Well, it turns out that if you study this in this lower dimensional shadow world, that indeed you have topological order. Well, this will go hand in hand with symmetry breaking in this shadow world. Okay, so you basically recover this whole Landau symmetry breaking paradigm by studying the entanglement degrees of freedom of your system, okay, which is indeed one dimension lower. It's a lower dimensional kind of representation because this lives actually on interface. This is an effective one-dimensional kind of system. And it turns out that all symmetries, dualities, all these kind of things, this matrix product operator algebras are exactly the right language for dealing with such things. Okay, so what are these matrix product operators? Okay, so these matrix product operators, they are basically just matrix product states, but instead of only having kind of legs on the bottom, you also have them on the top. So it's really an operator. It's like a density matrix, no? A density to go. It's very similar to what Roger kind of talked about, how to map, like I have a wave function, how do you kind of go to density matrix as well? You just put both legs on top and on the bottom. I'm sorry. And this gives rise to matrix product operators, and basically you have an algebra of such matrix product operators. And it turns out that if this describes symmetries in your system to describe topological phases of matter, these kind of operators, they form a closed algebra, okay, with structure factors NABC that actually do not depend on the system size. And this NABC are some data that turn out to kind of completely describe fusion categories. Okay, so what these tensor network methods give you, like this equation, okay, this equation here, this pulling through equation, this basically tells you, well, this is my PEPS here, and if I have this red matrix product operator, I can basically pull this thing through. If there's no physical action, this turns out to be kind of general topological order. Then there's some consistency equations. If I have this for one of these red things, and I have this for another red thing, then it turns out that I should be able to fuse this. Indeed, the product of these two MPOs is actually the sum of kind of these MPOs. So they form a closed algebra, and this is reflected in this tensor network. So we have explicit kind of tensors. We can actually do all of this on a computer. We have explicit tensor. There's a new tensor needed, this red kind of dot here, that allows you to fuse two tensors. And then you have associativity somehow of this, because all of these things are, again, these are just matrices. So if you have deal with matrices with operators, things should be associative. Then there's another object that you have to introduce an F, and then somehow this F has to satisfy something that's called the pentagon equation. So it turns out that actually these tensor networks, when you start describing topological phases of matter, and especially kind of symmetries in topological phases of matter, you automatically end up somehow with the representation theory of fusion categories. And this apparently seems to be kind of new. Okay, so what happens is that these matrix product operator symmetries and actually the related kind of wave functions that describe these PEPS wave functions, they are labeled by some kind of a set of tensors labeled by F0, F1, F2, F3, and F4. So there's like basically 5 different tensors. And it turns out that somehow the equations, the pulling through equations are in one-to-one correspondent with something that mathematicians have been studying for a long time ago already, and these are called bimodule categories. Okay, so there's somehow they define the algebraic data of something that's called a bimodule category M. And for people that are familiar with conformal field theory, it turns out, as I will kind of show later, this is well known somehow that these bimodal categories are basically kind of allow you to classify somehow the rational CFTs. This was famous work of Runkel, Fuchs, and Schweigert, and I will come back to this if I have some time. But anyway, so this whole PEPS formalism. So we didn't know any of this. It just comes out of this. These equations that we get turn out to be equivalent to this, but this is so a very natural kind of framework in which you kind of start studying the symmetries of these tensor networks. And if you choose, for example, all these F symbols equal to each other, you end up with something that's called these Levin-Wendt string nets. You also have like quantum doubles. There's also kind of intertwiners that allow you to kind of understand how to map all these different kind of models to each other. Like you have like quantum doubles and a related kind of rep model of Levin-Wendt string type, is there kind of a local quantum circuit that maps these models to each other? Well, it turns out that actually using these tensor networks, you can perfectly well do that and exactly show how to kind of construct such tensor networks or such kind of quantum circuits. Okay, so then of course, when you have topological phase of matter like these Levin-Wendt models, these string nets, we know that actually if you put your kind of systems, these topologically ordered systems on surfaces with non-trivial genus, you get kind of interesting topological sectors. Okay, and what are these topological sectors? Well, it turns out that again, these are then a little bit more complicated kind of matrix operator algebras that are called actually Ocneano tube algebras. Okay, and with this you construct somehow all the possible ground states, all the possible topological sectors, and it turns out that these are in one-to-one correspondence with the way you represent kind of anions in your system. Okay, so all these, of course, these topological ordered systems, all these Levin-Wendt string nets, but of course much more system than that, are so fascinating to condensed matter people because somehow you get these fractional excitations, you get these anions that are actually the elementary excitations. Well, it turns out that in this tensor network language now, you can construct these anions explicitly. And so when you construct this explicitly using somehow these matrix product operators, you can understand topological spin by just you rotate these things and you get these fractional kind of topological spins, you get braiding, all of somehow these things that actually I never really understood in this very abstract language of category theory become very tangible because you have actual tensors by which you can deal with this and you can actually construct these systems. Okay, so like an application that one of my students kind of had in mind, and is Alexis Schotte and collaborators. Actually, we constructed then actually a completely novel type of quantum error correcting codes by exactly using somehow this whole formalism. So this was a long kind of open question in the field of quantum information. Is it possible to use somehow these exotic methods or these exotic systems, not if you have physically anions, but really as somehow just a spin 1/2 system. I have qubits, and I realize actually such a string net in terms of my qubits, can I use this for quantum error correcting codes? And you can actually do this, and the fantastic thing of these quantum error correcting codes that somehow you build using these string nets, and for which you actually needed this whole tensor network language, is that these are universal. You don't have to kind of do this magic state distillation, and you don't have to kind of go outside of your kind of code space to do universal quantum computation. So for kind of resolving problems like this, you really need somehow this full kind of tensor network language to actually simulate this and actually prove that there is indeed thresholds using such kind of such error correcting codes. But let me kind of, the last minutes, try to kind of show you what direction we are going to, or what somehow I find very exciting in this very tangible way of understanding tensor networks. So it turns out that actually these string nets, or these Levin-Wendt models, they're well known to be related to topological field theory. Okay? These are basically, they're very strongly related to the Turai-Viro state search, and there's like a whole framework, of course, that started in quantum field theory that relates all somehow these things to each other. So there's topological field theory. Then turns out that people like Moore and Zyberg understood that actually the right language of connecting topological field theory to conformal field theory is actually modular tensor categories, and there's lots of kind of beautiful works that relate these things to each other. Also, Witten, of course, had understood very well that if you have a topological field theory, that actually if you look at the border, the border of these systems, you get effective like CFTs. So somehow from the mathematical point of view, it's very clear that somehow all these things basically are described by the same mathematics. Okay, so this is all kind of in the continuum. So what these tensor networks, and especially also, of course, the work of Kitaev and Levin and Wendt do is actually look at these topological phases of matter. This is by putting these things on the lattice. So that's the question: what survives of these topological field theories if you put them on the lattice? And these are these quantum doubles, string nets, and so further. And of course, there's also like the conformal field theory side, the lower dimensional side of this case, in which you basically describe critical and anionic spin chains. And this dates back to kind of old work of Pasquier and actually has recently kind of there were beautiful papers of Dave Eisen and Paul Fendley and collaborators, where they basically try to kind of see that indeed somehow critical spin systems are very, very strongly related to these tensor categories. It turns out that using these tensor networks, there's a very easy way of mapping, basically, or a direct way of mapping these string net models to these critical spin systems. So these string net models are 2+1D kind of systems that are topological ordered. So there's a big gap. There's nothing really kind of there's no kind of correlation length in the system besides having interesting anions. What you have here is actually a 1D quantum critical point with kind of power law of correlations, and or a 2D classical StatMech model that has power law decay of correlation. And it's not entirely clear how you would map these things to each other. Well, it turns out that there's a formalism that is called strange correlators that does that immediately for you. And this is basically implementing something that Fuchs, Runkel, and Schweigert kind of had a whole series of very famous papers around 2000, kind of formalizing, really from a mathematical physics point of view, this connection between tensor categories and conformal field theory. What this actually does, these tensor networks, I mean, this is actually a collaboration with them, is implementing this map on the lattice such that you can actually still kind of do these things numerically. Okay? And so indeed, somehow what Fuchs, Runkel, and Schweigert kind of discovered in this series of papers is that actually modular or module categories, somehow the model categories that basically popped up when you were describing symmetries of pepsis are the right language. So I don't really have time to go through it in detail, but it turns out that somehow they use these bimodules to describe CFTs. Okay, so they basically said that you need kind of different kind of categories, and you need some modules, and using all this, by combining all this, you can basically describe all possible kind of ways in which all possible topological features of CFTs. Well, what happens now is that it turns out that this mapping from topologically ordered states to critical wave functions or critical systems so this is like 2+1D quantum, this is 2D classical, can very easily be done by just kind of projecting this wave functions. This is a wave function on a large Hilbert space. What you do is basically just project all your physical degrees of freedom on some product states. Okay, so this gives you then a partition function of a classical StatMech model. Okay, because you start with a wave function in 2+1D, but basically you get rid of somehow your physical Hilbert space. You project all this physical degrees of freedom on some non-trivial product states. It's just product states everywhere you project this on. And what this is then is the partition function of somehow a classical StatMech model. Okay, and turns out that actually all these string nets are like all the famous integrable kind of spin system StatMech models in 2D can be kind of obtained by indeed starting from such a string net and devising or kind of choosing this strange correlator in a fiduciary kind of in a good way. So these Ising models, hard hexagon models, RSOS models, IRF models, all these models that people like Baxter kind of solved exactly, and for which somehow that form the basis for understanding criticality in 2D classical StatMech. Turns out that somehow this is a one-to-one relationship between these string nets. And of course, what happens if you project these things is that, of course, these symmetries, these matrix product operator symmetries, they completely survive. It's not because somehow you projected the physical degrees of freedom that somehow these n matrix product operator symmetries disappeared. And these are exactly all these dualities that people talked about. People like Kadamov had fantastic papers, or in the beginning of the 70s, like Kadamov and Seva, in which they kind of talk about disorder operators and dualities and all these kind of things. Well, it turns out that these matrix product operators, if you interpret them now from the point of view of somehow this StatMech model that is critical, is somehow the one that is responsible for the fact that it's critical. So what happens in your critical system is that you have kind of enlarged symmetries. Namely, suddenly you get these matrix product operator symmetries that are only there in the critical point. Okay, and it turns out that indeed kind of understanding symmetries of these tensor networks is the key in unraveling somehow the full somehow topological content of your conformal field theory. Okay, so in a very recent paper with my student Robin van Hove and collaborators, actually we did this, let's say, for the critical three-state Potts model. It turns out that this is actually very complicated to do it right. Okay, it turns out that the Potts model itself is actually not a modular. Somehow the fusion rules of the Potts model does not give rise to modular categories. So this is actually the right module. You have to kind of find other kind of categories to connect them to construct all the possible topological sectors. It turns out that there's like many different topological sectors. You have 8 types of defect lines, many more tubes. somehow all of these kind of things can now be done explicitly. And as far as I understood, this had never kind of been able, nobody had really done that, because the Potts model, if you kind of naively write it down, you would not write it down. You would write it down a representation that lacks basically all these different kind of types of symmetries. And you have to do this to basically extract all somehow the possible spectra out of this. But my time is really running out, so now basically for all possible topological sectors of the Potts model, you can get somehow your towers and understand somehow the full kind of content. You can also kind of do things on the cylinder, understand somehow how boundary kind of conformal fields, somehow the different boundaries are mapped to each other by kind of implementing or multiplying this with these matrix product operators, and so further. So, but I'm really running over time, so let me kind of just conclude. So I wanted to give you an overview of basically the research that's being done in this field of tensor networks. So there's both a very kind of strong numerical component, but also, like, I think a very interesting theoretical component. And this is somehow the magic, and I think the really kind of unique thing of these tensor networks is that these things go at the end hand in hand. At the end, kind of these matrix product operators, you actually need them if you want to simulate somehow your kind of Potts model in the right sectors and understand somehow all the different kind of boundary conditions that these things have, and to construct these boundary conditions. So of course, there's lots of challenges left. Okay, so we want faster, more robust TAPS methods. We want to extend this, of course, not just this matrix product operator symmetries to 2 dimensions. We want to actually do this in 3 dimensions. These would become kind of membrane symmetries. We want to kind of completely develop this whole theory. There is still kind of an issue with chiral topological order that we do not completely kind of capture. And of course, this is actually related by the fact that if you have chiral topological order, that this is actually kind of coming from a higher dimensional kind of system, like a 3D system. We would like to simulate lattice gauge theories, understand all the Wilson loops, all the somehow the defect lines, and so further. So, but anyway, let me kind of end with this picture that took me more time to make than actually the whole talk. And thank you for your attention.
So thank you very much, Frank, for such an interesting talk. It's open now to questions. Please, do you have questions? Yes.
So I have a question.
Please, go ahead.
Yeah. So Frank, very nice talk, beautiful summary. Just to get a feel for the matrix product operator set. Suppose I give you AKLT wave function, the AKLT model ground state wave function. It's a very beautiful, simple matrix product state. It can be written as a matrix product state. Can you motivate your matrix product operator from starting from that state, because that state has just one matrix?
Indeed. So the AKLT model and these A's are basically the Pauli matrices. And this U of G would basically be, well, you could say this, what is the symmetry? It's like the spin 1 representation of S2, which is actually SO3. Okay, so basically you have an SO3 symmetry. But of course, these Pauli matrices, they transform projectively according to this X of G. So what happens actually, if you look somehow, what you get here is a spin 1/2 representation on the virtual level. What happens if you multiply somehow these spin 1/2 representations of that correspond, which is a projective representation of this of your physical SO3 symmetry. So it turns out that this does not form a representation of SO3. It only forms a representation of SO3 up to a sign, up to a plus-minus sign. Okay, and this is the whole point: is that this minus sign is something. It's either plus or minus 1, and it cannot be anything else. And therefore, whenever you have something like an index that is labeled by an integer, it must be a topological index. Okay, and so the fact that this transform according to half kind of integer representations, while your physical degrees of freedom transform according to integer representations, actually shows you that there is something topological going on there. Because if you want to transform this model to something that for which this would also transform to an integer representation, this index would disappear. This plus or minus sign would basically become always +1. There would always be a gauge in which somehow it disappears. And therefore, there is no kind of continuous way in which you can suddenly kind of go from a 1 to something like a 1 and a -1. And of course, like this is an SPT phase. This is only true as long as you basically have a matrix product state that's protected. If you kind of say, like, I'm only interested in the Hilbert space of wave functions with a certain global symmetry. Whenever you kind of are allowed to break that symmetry, then it turns out that all kind of in the bosonic case, all matrix product states are connected to each other. This is actually not true if you kind of introduce fermiots in the case of fermions, even if you don't have any physical symmetries, it turns out that there's actually two different types of matrix product states. I did not talk about this at all. There's something that's called graded tensor networks, by which you can actually see that there's indeed two kind of completely different types of graded tensor networks. And of course, this corresponds to the Majorana case, the Kitaev chain, and somehow the normal kind of case for fermions. But this is in the 1D case. Of course, these matrix product operators are exactly the two-dimensional version of that. Okay, so they are exactly somehow what you have in 2 dimensions is that this would be this X, but it has an extra kind of index also in the other direction. So it has actually these things are connected to each other, and for systems that have non-trivial topological order, it's very important that actually these extra degrees of freedom, these fluctuating degrees of freedom, are there for kind of capturing the symmetries in your system. So, for example, like as I explained, then at some point you will map this to something like a CFT or a critical stat mech model. Well, then somehow these things could, for example, mimic the Kramers-Wanier duality. Okay, so this would be something like that. It would be like this matrix product operator would effectively implement something like a Kramers-Wanier duality, which is very, very similar actually to a Jordan-Wigner transformation. So it's like, so these are non-local operations that somehow non-local symmetries that emerge in these systems.
Thank you. Fascinating.
Shashwa?
Yes. Can you hear me?
Yes.
Okay. So you mentioned before that PEPs could be used to describe certain Fermi surfaces. So can you also use PEPs to describe, say, a system with a Fermi arc? Or for, say, example, a pseudo-gap phase?
So wait, are you? What is a Fermi arc? I'm actually not familiar with this. So this is like, of course, the Dirac point is easy, but it's, what is a Fermi?
So it would be like an incomplete Fermi surface. So some of it is like a disconnected Fermi surface. It might be seen like the pseudo-gap phase of certain Kubrick superconductors.
Yes, well, this is indeed problematic. If you want to use a unit cell, if you want to use a PEPs with actually one that has a very small unit cell, so you would need actually to break your translation invariance and start working with bigger unit cells, such that you basically have some fractional filling of these surfaces. So certainly for simulations with PEPs in the thermodynamic limit, indeed this is problematic if you kind of are in incommensurate kind of fillings. But as long as you fill with some kind of fractions, that should be possible. But you will have to use kind of big unit cells in your PEPs.
Mm-hmm. Okay. Okay. Thank you.
Okay. Further questions, Manu Kumar?
Yeah. Thank you. Nice talk, Frank. So I have one question. What is the status of temperature dependence and also the dynamical calculation in the PEPs?
Yeah. So it's a very good question. So what happens at finite temperature actually is that typically the ground states are the hardest. Okay, so at finite temperature it's actually easier to write down tensor networks, and there has indeed been quite some progress there in relating cluster expansions to this kind of tensor network language. I don't have any slides about this, but it turns out that actually all these ideas of cluster expansions can be adopted to the framework of tensor networks to construct very efficient kind of ways of writing down thermal states of strongly correlated systems, both in 1 and 2, and then actually also even in 3D. The dynamics, on the other hand, is of course something that is much more problematic. So working basically in the real time and doing something like a quench, what happens is that the amount of entanglement kind of starts growing like extensively, and you would need exponentially large bond dimensions for capturing somehow the physics using somehow these tensor networks. Now, this is not necessarily a problem, because we know that basically what happens while somehow this entanglement grows so much is that these correlations will become basically completely invisible, because somehow they become embedded in the multipartite correlations of your system. And as long as you look at kind of few body correlations, you would never basically be able to distinguish the fact that this is very highly entangled or it is thermal. And it's one of the big frustrations for anybody working in this field of tensor networks, that nobody has really come up with a way of converting indeed this real-time evolution into an evolution that actually kind of maps pure states to mixed states. Okay, because this is physically what is going on. Now, if you have like a system that creates kind of extensive amounts of entanglement, okay, so that you get volume loss, effectively what happens is that you can describe this whole system with the thermal state, with somehow a finite, with a state that has a finite entropy density. And these states can, of course, very well be represented using matrix product operators, just because I said they are just like Gibbs states. And but nobody has been able to go up with an algorithm that we would say, yes, this is actually kind of showing that how this thermalization happens. So it could actually be that before you thermalize, you have to go to kind of very, very highly entangled states, and then before you can actually kind of describe your systems with the thermal states. There are actually very nice works of people like Dubai, where they have some field theoretic kind of arguments why this would be like that. But it's still, this is certainly one of the big frustrations of people in the field of tensor networks, is that we still don't understand how to kind of simulate this and how to kind of turn entanglement into entropy.
Okay, thank you very much.
So further questions? I have some questions, Frank. I have several questions, but I will ask you, perhaps the most challenging one. So going back to dualities, many of the things that you were talking about, one can obtain by using the technique of bond algebras, okay? So you don't need to go, you work directly with the model, with the Hamiltonian or with the partition function. If you have a classical system and you apply the bond algebra techniques, which smells similar to what you are doing, but you are doing at a different level. You are doing at the level of the tensors. Okay, so and not at the level of the algebra of interactions, although, some of the interaction is encoded in the tensor, but, the interactions may involve, longer range things, for example. So my question is, what kind of advantage I can get by using this approach that I cannot get by using the bond algebra technique? Okay, and in particular, the reason why I'm saying is that it could be, I could imagine some cases, this is what I could imagine. Suppose I have a model that is very complex and I don't know how to really solve that model. But I have some very good, I suspect that there is a very good tensor network representation of that model. It may happen that indeed, using your techniques, I can derive some dualities. Using your technique on your tensors, I can derive some dualities to some other model that, by using the usual bond algebra, is hard to see because I'm using the bond algebra of the real model. Okay, but by using the tensor network, that is, you assume is a very good approximation, you may be going to another model that indeed is, not very far because it's in a low energy sector in some way of your theory. So that kind of advantage I can see, but is there any other advantage of your way of doing things with respect to the bond algebra? Because to me, it smells very similar.
Well, like certainly for this example of the POTS model that I showed you here.
That's a very good example. With the bond algebra, you do it in 2 seconds.
No, but you don't get all these defect lines. I don't think you get somehow these.
Absolutely.
You don't know how to construct somehow the 8 types of defect lines using the bond algebra.
Well,
because you get actually, you really need somehow these different kind of labels from this category, because actually the POTS model themselves is not a model category. So it turns out that actually to get all your symmetries, as far as I understood, you really need to kind of do it in this language to understand basically all the symmetries of the POTS model.
Yeah, no, you can do with the bond algebra. What I don't know, because I didn't think about, is these 8 type of defect lines. That's a point well taken. I would like to understand. That's the reason why I'm asking you the question. What do I gain? Okay, because for example, what the bond algebra doesn't give you directly is, for example, the string operator. Suppose you have something that has topological order in some representation, and now I want to know what is the string order or the brain order, okay, in the dual representation that has topological order. So the bond algebra, if you know some lambda order in some phase, then through the bond algebra, you can get the string or the brain order. But my question is it possible that even if you do not know, with your technique, you do not know the lambda order in some representation, you can get the string order by using your technique? because that is a difference. Because if you can get all the string orders, I have a challenge for you. If the answer to my question is yes, you can, then I will ask you, okay, what is the order parameter of QCD? So take a Yang-Mills theory and now tell me what is the order parameter of QCD. So what is your answer? So can you get string and brain orders from these tensor network techniques?
Well, yes. So that's exactly the kind of questions that we want to ask. Okay. So for QCD, I don't know. I don't know enough about QCD, and of course, people, I don't think that the answer is known. So first, a disclaimer. I'm not claiming here that, of course, that we are discovering new kind of critical models. Okay. So people in the CFT community, they all know somehow that this has completely been understood somehow, this whole language. So this is exactly somehow the work of Schweigert and Fuchs and Fuchs and Runkel and Schweigert. They have basically done that they have classified all these CFTs. They have understood how to kind of what the defect lines are and these kind of things. What was not understood, as far as I understand, is how much of this survives on the lattice. Okay, so how do you actually start doing this in a tangible way on the lattice? Even if I give you a model somehow, how can you understand all these topological defects? Okay, so our motivation was to understand all of this, to understand all the dualities. Okay, so there is this amazing net of dualities. Now, if you kind of look at StatMech models, there is this kind of notion of you have the 6 vertex models, you have the RSOS models, you have all these kind of different ways of describing the same CFTs, okay, the same critical theories, but with completely different degrees of freedom. And we wanted to understand this from the point of view of these tensor networks. Now, it turns out that all these different dualities correspond to intertwiners that you kind of relate to this fundamental theorem of Pep's, no? That you can construct actually these matrix product operators that map one model to the other model. You can map models that actually somehow, in one case you have a quantum group symmetry, in the other case you have somehow these category symmetries, and we understand now how to kind of do this. So our motivation was to understand this extremely kind of well-known literature from the point of view of these tensor networks. And of course, the goal is to use them then into kind of non-trivial numerics. Like we say at the end, this is kind of not just related to CFTs. We can actually also do this for models that are not integrable, for things for which people have no kind of exact understanding. Okay. Also, all these techniques, we would like to understand what happens in higher dimensions. No? So there is a priori no reason why somehow these matrix product operator symmetries cannot be generalized to somehow Papal symmetries. So this is where we are kind of working towards. So of course, we are just rediscovering things that many people have already discovered for a long time ago. Like forgot how you called it, the bond order? No, the bond order technique? No, the
algebra technique.
The bond algebra technique. I actually don't know what this is, but it probably has kind of, it might be very similar to this. This is well possible, although certainly for this POTS model that I just talked about, we have kind of, or my students have done an extensive literature search, and we have never seen anything like that. We have never found any kind of place where for the POTS model, you actually kind of can construct all these defect lines and all possible topological kind of sectors of these models. But I would be very interested, of course, to discuss further with you. We should do this probably offline, but
yeah, sure. No, sure. I have several questions, but they are very technical questions. So I prefer that other people ask questions and we can continue offline. So is there any other question? No? Well, if there are no more questions, thanks a lot, Frank. I mean, excellent talk. I always enjoy talking to you. With this, I mean, we close this session. So we expect that you can join us next week with a quantum information, quantum computation session. Okay, guys? So have a nice week. So, and Frank, we can chat off the line, I think.
Yes, let's do that. Today or another day?
We can chat another day. Don't worry. Yeah. Go and relax.
Perfect. Yeah, perfect. See you soon.
See you. Bye-bye. Thank you.
Thanks a lot. Thanks for inviting me.
Oh, thank you.
Bye-bye.